Hi, this is Gary Fuspart. I'm going to tell a tale of woe and intrigue about the development of this PC board, which is a device I made to enhance my nearly 50-year-old TRS-80 Model 1, which more or less still works. I do have some problems with it, which I'll get to in this tale, but what I was attempting to do was to make an interface to this TRS-80 that will plug into the expansion connector on the back and allow it to generate printer output. The TRS-80 defines a standard for how to interface with a line printer that's the software expects it if you have disk operating systems and whatnot. It will expect the printer to be in a particular place as a port. I custom designed this board. I'm starting at the end of the process because the board is now complete, but this shows the basic nature of this board. I developed this board by hand, old school techniques, through-hole soldering onto a vector strip board. I developed a couple of tools for testing the process as I went along so that I could make sure it wasn't going to do anything catastrophic to my computer when I plugged it into it. In 1977, when the TRS-80 was originally sold, if you wanted to plug a printer into the computer, the official mechanism provided was that you had to buy an additional $600 expansion interface box. Now that box would allow you to connect up things like disk drives, but it was the necessary minimum officially supported way to provide for a printer that would connect up with a standard Centronics parallel printer interface. Well, $600 was quite a bit much for me, and I decided to homebrew design a way around it. This was the monster that I came up with. It was based upon having several individual plug-in boards that I hand-designed, hand-wired, and built. And it was successful at the time. I made this in about 1978. In the process of building and testing this board, I had to go through a number of adventures in the wiring of the board, point-to-point wiring with little pieces of old telephone wire, hand soldered onto many points of contact, and fixing little problems that came along, accidentally wiring the braces in the wrong place, fixing those problems, coming up with a testing scheme and building a board that would test the process. But some of the stories of how that process went, I'll get into, because some of the most interesting problems I had were instructive in how to diagnose it and how perhaps to avoid the problem in the first place. As part of the project to make the TRS-80 printer interface, I wanted to test the logic of the decoder section and make sure that all the signals were being processed properly before I plugged it into the TRS-80. Didn't want to do any damage to the TRS-80. So I rigged up a tester scheme. This board plugs into the same connector that the TRS-80 cable plugs into and generates a static address with the jumpers in the correct position here. It generates an address 37E8 hex, which is the address of the printer port. If I move those one or both of those two jumpers there, the address will be somewhat different because the generate zeros instead of ones, at which point the address decoder section will not decode to the correct address, and so the writes should not carry through to the other side of the port. The port can only write if you generate the correct address and generate a write signal. I've wired up a set of lights so that I can take the data port, which has been hardwired to generate a hex 69, which comes out as a lowercase I. The pattern doesn't mean a lot, except that I was trying to make one that I could tell me something later when I was trying to force data on the port back from the reading of the port, and that seemed like a good idea at the time. At any event, I have to plug this in to an outlet. Once I do, I now have a pattern of lights on here which shows a 01101001, which is a hex 69. I'm showing you that first because that shows what goes into the port. When I strobe the write signal, that should be transmitted to the port. Okay, now I've transferred the lights over to the back section of the board, so it's showing what's going out of the latches on the port. Now, this data is latched. If I hit the reset button, it should clear to 0. And it does. Now that I've cleared it to 0, the thing's in a ready state. If I send data to the port, it should show that 6-9 pattern again. If I go over here and take this jumper and I put it onto the right strobe, essentially I'll run a low ground to the strobe line. And as you see, it transmitted data to the port. The data to the port, if I then reset it, goes back. The strobe line cleared, the data cleared. So the loop that the processor is supposed to use is to watch the strobe line. When the strobe line comes on, it then processes the data that it finds, because the data was latched at the same time. And then when it's done processing the data out the serial port, it resets everything by bringing the reset line low, and that resets everything to 0 on the data port, but it also resets the signal that the TRS-80 is supposed to read to say the printer is busy or not. At any event, what needs to be done now is to test the board. Since the board appears to pass a static test for the sending data to the port, it needs to be tested with a Nano in place, programmed to read that data and process it, and have the computer send data and see what happens. Okay, this is my old TRS-80 Model 1. I've been attempting to build a printer extension, a custom printer extension board for this thing that I've been designing. This is the board so far. I have tested it with chips populated on the board, and so far in standalone tests it looked like it was doing pretty well. But when I plugged it onto here, let me show you. This is what I would expect to see when I turn on the TRS-80. It says limit. If I hit enter, it'll get Microsoft Basic. Okay. That's TRS-80 level 2 basic, Microsoft Basic. Okay. The concept is this extension cable here plugged into an edge card connector on the back. I should be able to plug this cable into this board and have everything work. Okay, this is the cable plugged into the board. This is what happens when the cable is plugged into the board. No parts, no power. I get gobbledygook all over the screen. Looks like a catastrophic error. Looks like there's something really, really wrong with the board. Okay, I've tried a number of things. I tried actually checking the cable continuity all the way from the edge card connector. This is the edge card connector. All the way down the cable to the connectors. Could not find a problem, but just in case I was having a contact issue, I went ahead and reattached. I cut some more of the cable off and I reattached a header connector on the end. Still the same results. And I double checked all the connections between the header connector and the board. Found no problems. I went with an ohmmeter over this entire 2-wide header port, 40 pin header. I went through all the pins with an ohmmeter looking for shorts across connected two pins close to each other in all directions, and could find nothing at all. I could find no reason that there's a problem with the connector. So that leaves all the connections going someplace. Well, it is a manually wired board. There are some cables all over the place. It's relatively compact and flat. I didn't think I was going to have an RF problem or something, but it's possible that I've got a radio frequency problem, that this design may just be problematic and may not be workable. And I was getting really desperate to find something, some way to deal with this and find out what was going on, because if it's a radio problem, if there's just an inherent flaw in the design, then I'm going to have to pitch the whole thing. But it was working so well in static tests with a tester that with individual things, it was clear the latching was working, the data was getting sent through, the strobe line was working fine. I really don't want to give up on this thing, so I tried to think of a way to test what was going on. And it hit upon the idea that if I could isolate the pins on this connector so that I could selectively turn off pins going to this thing and see if there's a problem with any given pin or any group of pins. First thing I thought were the data lines. How do I disconnect the data lines? Well, I thought about it for a while and realized I have a bunch of these Arduino style connectors. If you make an Arduino shield, you tend to use these things. That way you can have the lines stick out the bottom of a shield board, and the sockets up at the top, you can plug another shield into it and you can stack shields up. That's what those things are for. And I have a box with a few of these in it. And I realized if I plug these into the end of the connector, the cable connector, I can use the fact that some of these pins are connected and some of them aren't to isolate the pins. And that way I could test and see if I would get the same symptoms with all the pins, with some of the pins missing, or essentially eventually isolate the problem. Okay, this is an example. I've plugged a couple of 10 units in here, so I've got 20 pins across on one side of the connector. Now this particular side of the connector, I've verified that I've wired the thing correctly, that the cable, the edge card connector to the TRS-80 is correctly going to the places I think it's going. So according to that, this is the row of pins that includes the data lines. Now I'd actually tried it with and without the data lines and found out it didn't make any difference. I'll show you what happens when I plug this in. Now what you see here is just the one row of connector pins connected. That includes all the data lines, some of the address lines. The read and write signals are on the other side. But if I turn on the computer, I get limit and Microsoft Basic. Computer's working. Ah! It's not the data lines. And it's not, at least not the address lines that I've uncovered so far. So let's keep going, and I'll try some other thing. Okay, long story short, I've, after testing exhaustively, leaving some lines open and some lines closed, I now have everything connected except one pin. This pin is associated with the address 12, A12 line. I'll show you what happens when I have everything except A12 connected and I turn it on. I get what I expect. Okay. Just to further prove the case, I'm going to bend this pin back so that it makes full contact and plug it back in and demonstrate that with all these connectors in place, the original error it returns. Okay, at this point, all the pins are in there. So now I should have the same results as I had when I plugged the entire cable in directly rather than through these extra Arduino connectors. Now, all the connectors are back on. If I turn it on, I get the gobbledygook. So I have proven the case that whatever the problem is, and I still don't know what it is, but I do know that it's related to the A12 line only. So this is an example of how to use an unconventional technique, but these little Arduino connectors allowed me to get into the cable effectively and turn on and off signal lines. That's not something they were designed for, but it sure did me a favor this time. It was almost difficult to believe that this was the error. There is a teensy tiny sliver of copper foil that I did not completely cut through with the Dremel tool. It left a tiny little connection between the connection on the correct pin to which A12 was connected to what was actually the +5 supply. With that happening, the +5 supply connected directly to A12, it caused the symptoms we saw. Essentially, A12 was just bollocksed. I'm going to try to get a microscope on this and show it before I fix the problem. Now, having found the tiny little sliver that was cross-connecting A12 to the +5 line, and having fixed that, I cut the trace, cleaned it up a little. I took the liberty to add a couple of extra little features. I've rigged it so I can put the power off of the Nano rather than the TRS-80. I found out that the TRS-80 really isn't supplying a sufficient amount of power anyway. The tester that I use still powers from that, so I put a jumper on to allow me to be able to choose which power source when I'm testing the board in a static test. At any event, here goes. Newly fixed board. Yes. Microsoft Basic. The board by itself doesn't interfere with the ability to boot the computer. Next, I've got to populate the board with chips and verify that that doesn't cause any trouble. Okay, for the time being, I populated with chips, leaving off one chip, the chip that's the octal buffer that controls sending data back to the TRS-80. I'm not certain whether that one, the testing was inconclusive, and I wasn't certain whether that part of the circuit was actually working correctly, and I don't want to interfere with the operation of the TRS-80, so I'm leaving that one unplugged for now, because that way it shouldn't have any effect on the data lines if that chip isn't in there. So I'll verify that it comes on, and it does. So far so good. Looks like the Nano is getting a little bit of back power from the system, but it's not actually being powered by the... If I plug it in, I'll have to test it. I'll have to test it by plugging it in to a computer and see what happens. Okay, the actual testing of the printer interface. The Nano's been programmed to send characters that it sees on the port out to a serial port, and I've successfully gotten a couple of characters to send, but I'm hobbled by the problems I have with the TRS-80 itself. It's been acting flaky, and one of the reasons to build this thing was to get a verification as to whether or not it's the video section that's dying or whether the whole computer is shutting down. I don't really know. And if I can get this thing to generate a loop of characters that goes to the serial port without shutting down, even though the video shuts down, then that'll confirm the first hypothesis. If it doesn't work, if the loop doesn't send after the video shuts off, then it apparently is the whole computer that's shutting down. It doesn't seem to be killing the computer because it keeps restarting, but whatever its problem is, I don't know. One of the other problems I'm having with it is the keyboard is so bad. I'm having a great deal of difficulty getting a program typed in fast enough. I only get about 1 minute to test this thing before it dies. Now that was enough to get a couple of characters to go out by simply poking to an address, but what I need to do is type a very short program, but the problem is that the keys keep messing up on me, and the computer stops working before I can get the program loaded. What I want to do is get a program running in a loop that sends a stream of characters. Okay, so far so good. I've got a stream of characters coming out. I've got sending an E's to the serial port. It's sending them out about 3 times a second. Let's see what happens. This board is doing the job. The Nano is watching the port. If it sees an E being transmitted, it broadcasts the E. I haven't implemented the actual, I haven't tested checking the port for busy yet. All I'm doing is sending stuff to the address 378 hex, which is 14312 decimal. So this program right here running is sufficient to test it. Now it's getting flaky. Aha! So far so good. The video is dead, but it's still sending characters. That seems to confirm that the problem is with the video stage. This is very useful information. I don't know what it's going to tell me how to fix it, but this is a test that I haven't been able to run before because I had no other mechanism to verify that a program was continuously running. The only way that this thing would keep putting out characters is that the TRS-80 is continuing to send them. Okay. My original hunch is confirmed. It appears to be the video output stage causing a problem. Whether or not that's fixable, I don't yet know, but hopefully if I can get this whole thing to work while the computer is disassembled and on the bench, if it can work under those conditions, then I can start investigating what's happening at the chip level. Okay, I put the other chip in, the buffer that's supposed to read data back. It doesn't seem to be doing its job because all I'm getting back is a 255, and that should have had a 0 in bit 7 most of the time, because a 1 in bit 7 would be busy, I should also have some 0 bits showing up. Something isn't working by expectations there. Since it seems to be staying up, I changed the program so that it would print more characters to the output and do it a little bit slower so that it should have enough of a delay that it doesn't really need to check if the printer's ready. It's going to get 1 character at a time. That should get rid of some of the double characters. Now what I've got over here is a stream of the printable ASCII characters. I must say I'm kind of amazed. This thing is still running after more than an hour and a half. As you can see, it's still feeding characters. Now, I've given some thought to the problem where it doesn't seem to be reading the data properly. And I don't know for sure, but I suspect that I can improve things. Certainly I can try something. It took me a couple days, but I finally figured out what I was doing wrong to read the printer buffer status. But one of the things I do to try to maintain some semblance of order in the thing is I try to, when I'm doing a project which gets complicated pretty fast on designing one of these stripboard projects, is I try to use a graphical tool to figure out exactly how I'm going to lay the thing out, and I can have a front and a back copy that looks like the stripboard that I'm using. But as you see, it can get pretty hairy, and the documentation doesn't always keep up with my ideas. As you see, lots of scribbled notes all over the page. Sometimes the project gets away from me a little bit, and the data latches that I use, the 273 chips, obvious in style. Here you have D's are inputs, Q's are outputs, and the notice the D's and the Q's are all right next to one another. They alternate back and forth a little bit. You got a Q, D, D, Q, Q, D, D, Q on each side, but they're right next to one another. The inputs and the outputs are right next to one another. You know, to the data buffers, the tri-state buffers that would get data back when it was read. Notice the complications in this thing. There are actually multiple chips in a family, and the documentation is trying to do quadruple duty here for the kinds of variations of the chip, and it got a little bit confusing. And I tended to gloss over this a little too much. I was unfamiliar with this chip. I hadn't used it much, and I'm afraid I didn't pay sufficient attention to this, and I made a mistake in the design that I didn't pick up on right away when I looked at this. A few days later, while I was puzzling over the problem, I tried looking at another source for the same chip number, and somehow this looked less confusing to me, and I suddenly noticed something. Section here, I have the octal buffer chip. Now, notice that I laid this thing out, and I have Y's and A's. I have A's for inputs and Y's for outputs, and I have them showing them next to one another. Unfortunately, that was a mistake, because it turns out that when you look carefully at this diagram, the inputs for one side, say this side of the chip, which is actually the one that I was trying to concentrate on, I have a 2A1, 2A2, 2A3, 2A4. I noticed that they were turning things inside out. I saw the Y1, Y2, Y3, Y4. At least I caught that. But what I didn't notice was the 1 and the 2. The thing that makes this chip a little weird is that the inputs are on one side and the outputs are on the other, and they crisscross each other. But I didn't notice this crisscrossing, and so what happened is when I wired the board up, I had wired up the outputs such that they were going to the wrong inputs. And so what was happening was all the outputs were connected to the inactive side. That was all, they were all tri-stated. There was no output at all. I missed that detail. And when I realized my mistake, it wasn't too hard for me to figure out a way to deal with it, so that I fixed the board by rerouting some lines around and made sure that everything was lined up in the right place. Okay, after several days of work and modifications to the TRS-80 printer board, I finally have it fully functioning. This is an example of the output of the running program. I'm going to break the program and list it to the screen. Okay, that is the program. Make it a little more clear, I'll do a CLS first. Okay, now, because I now have the interface working correctly for the busy signal, I can do an LLIST, which is a line printer list on level 2 basic. And what that will do is it will list the printer, the program, to the printer, which is now the serial port. I'll do it a second time here, LLIST. And you can see that that means that it fully meets the expectations of the interface in the classic Model 1 system, where the printer port is and how the printer port works. So the project is, at this point, a success if I can only get the TRS-80 to stay up for a while. Since I successfully tested the line printer interface for the TRS-80, I've decided to add some finishing touches. I made a nice little acrylic case for it, put a label on it describing what it is. It protects it, makes it a little more rugged, looks nice. And because it's inconvenient to remove the board from this case, if I do choose to re-demonstrate the static testing with the board, I rigged it so that the board can more easily fit inside the case without completely removing the board from it by putting a notch in the side of the tester board. That makes it fit a little better. This is Gary Flispart signing off with another successful project.